Hello friends, welcome to the session. It's continuation of chapter 4 inverters. In the last session, I discussed about what exactly single phase half bridge inverter, and I discussed these waveforms also, how to draw these waveforms, how to analyze the sequence of conduction of devices, all this that I discussed. Okay. Now, but there is some drawbacks are there in half bridge inverter. One is output voltage is only Vs by 2 and it requires 3-wire DC supply. Efficiency is only 50%. Yes, these are the problems with the half bridge inverter. To overcome these drawbacks, then we are implementing the full bridge inverter. First we will see single phase full bridge inverter. What are the modifications here? Then later on we go for analysis of both half bridge and full bridge inverter. Okay. Yes. The continuation of this session with the single phase full bridge inverter. Single phase full bridge inverter. That you concentrate. Single phase full bridge inverter. Yes. First, we'll see what is the configuration of this full bridge inverter circuit. Having 4 switches and 4 diodes. This is the configuration we are using. We are connecting some load. Yes. This load current direction. This is a load voltage polarity. Yes. Yes. This is S1, S3, D1, D3, S4, S2, D4, D2. Let the supply voltage is Vs. This is a single phase full bridge inverter. The single phase full bridge inverter is having how many switches and how many diodes? This is 4 switches and 4 diodes. As compared to half bridge inverter, this is the number of devices are double, where 2 switches and 2 diodes, but here 4 switches and 4 diodes. That's why this full bridge inverter is combination of 2 half bridge inverters. It is combination of 2 half bridge inverters. Combination of 2 half bridge inverters. 2 half bridge inverters. Yes. Combination of 2 half bridge inverters. Yes. The combination of 2 half bridge inverters means. Yes. First I want to explain this concept for resistive load. Then remaining loads, you get the waveform same. Only The half bridge and full bridge is configuration is different, number of devices are different. Based on that configuration, output voltage will be changes. Here also we can get same waveform, but here instead of one device, how many devices will conduct? Two devices. That is the only difference. But output voltage is instead of Vs by 2, then we can get Vs. But remaining waveforms all are same. But voltage is different. Output voltage is different. In the sequence of conduction of devices, instead of one device, it will conduct two devices. That's the only difference. Okay. Now see, I want to explain this concept for R load. Okay. R load. We know that it is a voltage source inverter. Na? Actually, it requires feedback diodes, but except R load. For R load means no need of feedback diodes. No need of feedback diodes. Feedback diodes cannot work. No need of feedback diodes because it is a R load. Then remove the feedback diodes and redraw the circuit. Remove these feedback diodes and redraw the circuit. Yes, all of you redraw the circuit. Remove these feedback diodes. So this is full bridge inverter for purely resistive load. For R load, no need of feedback. Now on and off is in our hand. We can operate this circuit in such a way that we want to convert DC to AC. Yes, that for 0 less than or equal to T less than or equal to T by 2, I will turn on S1 S2. Okay, S1 S2 is on. S1 S2 is on. If S1 S2 is on means what is the equivalent? This is S1. You replace with this load is which load? R load. We are drawing the waveforms for purely resistive. Positive, negative V0, and this is I0. This is S2. Yes. Then apply the KVL for this loop. This is Vs. Then what we get? Enter at positive terminal, take positive V0. This is minus Vs is equal to 0. Then what is V0 equal to Vs? If S1 S2 is on, what is the output voltage we are getting? Plus Vs. Now one operation is nothing but a one time period of operation. Now what I can do means for T by 2 less than or equal to T less than or equal to T, I will turn off S1 S2. On and off is in our hand because input is DC. I will turn off S1 S2, then I will turn on S3 S4. S3 S4 is on. If S3 S4 is on, what is the equivalent representation? That you will see. Is plus minus Vs. S3 is on and S4 is on. This plus minus V0. This is S4. This is S3 and this is S4. The switches are like this now. It is conducting like this. Then apply the KVL. Then what we get? Minus V0 minus Vs equal to 0. Then what is V0 equal to? Minus Vs. That means if S1 S2 is on, output voltage we are getting plus Vs. If S3 S4 is on, how much output voltage we are getting? Minus Vs. Yes. You are converting unidirectional voltage into bidirectional voltage, that is DC to AC conversion. Same waveform, this is plus Vs and this is minus Vs. But here which device is conducting? S1 S2. Here which device is conducting? S3, S4. Here which device is conducting? S1, S2. Same waveforms, but the amplitude is changing. Instead of Vs by 2, we are getting Vs. This is for R load now. We know that for resistive load, voltage and current waveforms are same. Same points I want to list out here. For R load, for purely resistive load now, V0 and I0 waveforms are same. Okay, V0 and I0 waveforms are same. V0 and I0 waveforms are same. We know that it is a voltage source inverter. Except R load, it requires feedback diodes. Except R load. Except R load, it requires feedback diodes. Yes, it requires feedback diodes. For R load, I'm explaining this circuit without any feedback diodes. It requires feedback diodes. Except R load, it requires feedback diodes. Okay. Now, based on the load, same points what I given in half bridge inverter. Output voltage waveform independent of the load parameters. But based on the load, which waveform will be changed? Current waveforms are changing. That is output voltage waveform. Output voltage waveform. Because it's a voltage source inverter na. In the differences, that concept I explained. Output voltage waveform independent of load parameters. Independent of load. But output current depends on load. But output current depends on load. That means based on load, this output current waveforms are changed. These are the different waveforms for different loads. Different current waveforms for different loads. Okay. But here waveforms are same. It is a half bridge or full bridge. Waveforms are same. But instead of one device in full bridge, how many devices will conduct? 2 devices. Only configuration is different. Same points I am list out here. It may be half bridge or full bridge. Waveforms are same. Okay. Now tell me, here which device is conducting? Instead of D1, D1, D2 is conducting. Here which device? S1, S2. Here which device? D3, D4. Here which device? S3, S4. Again cycle is repeated. D1, D2. Here S1, S2. Here D3, D4. Same waveform for purely inductive load, but the sequence of conduction of devices is like this. Here also same. D1, D2. S1, S2. D3, D4. S3, S4. At a time 2 devices are conducting. D1, D2. S1, S2. D3, D4. At a time 2 devices are conducting. Here also same lagging load na D1, D2. S1, S2. D3, D4. S3, S4. Again D1, D2. S1, S2. D3, D4. For leading loads means first switch next to diode. S1, S2. D1, D2. S3, S4. D3, D4. Again S1, S2. D1, D2. First switch next to diode. Understood? This you note down. Quick. S. You write as a note. For lagging loads, for lagging power factor loads, What is the sequence of conduction of devices? The sequence of the sequence of conduction of devices. Tell me. The sequence of conduction of devices is, which is the sequence? First to diode, next to switch. But in half-bridge inverter, at a time only one device is conducting. But here two devices are conducting. Okay, D1, D2, S1, S2, D3, D4, S3, S4. Next. For leading power factor loads. For leading power factor loads. For leading power factor loads. Tell me, what is the sequence of conduction of devices? The sequence of conduction of devices. The sequence of conduction of devices. What is the sequence of conduction of devices? Yes. First to switch, next to diode. RLC, XC greater than XL na? RLC, XC greater than XL means, XC greater than XL means leading condition. Okay. The sequence of conduction of devices. S1, S2, D1, D2, S3, S4, D3, D4. Understand? Quick. Parallelly note down. Yes. Tell me. For R load, for any load, what is the waveform? Voltage, output voltage waveform is square waveform. Here we are generating square waveform, that's why I am giving square waveform. For any load, you also generate quasi square waveform. You also generate PWM waveform. Pulse width modulated waveform also we can generate. Okay. But here our analysis mainly square waveform that I am giving here. Okay. For any load, output voltage waveform is, because it is a square wave inverter, output voltage waveform is square waveform. Output voltage waveform is square waveform. It is a square waveform. For any load, output voltage waveform is square waveform. Okay. For R load, output current is, I told already, for R load voltage and current waveforms are same. Output current is square waveform. Output current is square waveform. Okay. Now I want to list out some points with respect to purely inductive load, L load. Same points what I discussed. Half bridge inverter. How much angle each device is, how much time each device is conducting? Either D1, D2 or S1, S2 or D3, D4 or S3, S4. How much time it is conducting in one cycle? Either S1, S2 or D1. This total is T by 2 na? This total is T by 2 means from this point to this point. How much? T by 4. Any device, it may be switch or diode. Each device conduction time is, each device conduction time. How much? T by 4. Same points what I discussed in half bridge. Yes. Time taken to reach peak current. Time taken to reach peak current. Okay. Time taken to reach peak current is how much? T by 4. Peak current means reference you take 0 from this point to this point. I am not asking about peak to peak current. Peak to peak current in the sense negative to positive. Peak current in the sense 0 to positive or negative to 0. That's why this point to this point or this point to this point you take. This point or from this point to this point. How much time it is taken? T by 4. If it is asked for peak to peak, how much time? T by 2. But I written only peak. Peak current, time taken to reach peak current is T by 4. If it is asked peak to peak means into 2 you can take. Then T by 2 you can get. Then time taken to reach peak current is T by 4. Then we know that VL equal to L into di by dt. Same formula I derived. L into current is changing from 0 to peak value. Final value minus initial value. How much time it is taken? T by 4 time. What is the peak current? Peak current equal to VL into T by 4 by L. For purely inductive load, what is the current? What is the current waveform? For purely inductive load, current waveform is triangular. In which inverter? Voltage source inverter. Off bridge or full bridge. That's why current waveform is triangular. Current waveform is triangular waveform. Yes, current waveform is triangular. Okay, this about what exactly? Full bridge inverter. Yes, note down quick. You know that except R load, for remaining loads, what we are using? Feedback diodes. This is low. This you already know. No need to draw. Except R load, for remaining loads, we are using feedback diodes. With the feedback diodes only, we are drawn that waveforms. This D1, D3, D4, D2. This over. Okay. This already no need to draw this one. Just a point note. These points you know. Yes. Here I want to discuss one small concept here. Continuation of this either half bridge or full bridge. Yes. Clear? Okay. Now you have the one doubt here. Sir, what is this lagging? What is this leading? Why the in lagging case first to diode next to switch? Why in leading case first to switch next to diodes? How the diodes are conducting? How the switches comes into the existence? What is the purpose of using these diodes? Okay, all these doubts you have. The operation I explain, how we are getting the waveforms I explain. But in the concept point of view, you have the one doubt. Sir, what is the need of these feedback diodes? Without feedback diodes, is it possible the operation? Yes, possible. Operation is possible. But it is unstable operation. Understood? Sir, how these diodes will come into the existence? Why you are telling that if it is a lagging load, first to diode, next to switch. If it is a leading load, first to switch, next to diode. How it is happening? Okay, that we will see. That doubt I will clarify by using this explanation. Okay. So, okay, clear? All these points list out now. That we are operating this circuit for RL load. If it is a purely resistive load, there is no function of any diode. Feedback diodes cannot function. Let for that I am explaining one example using RL load. Let it is a RL load. This is positive negative V0. Let assume that initially what I am doing means I will turn on S1 S2. Let assume that initially I will trigger the S1 S2. If S1 S2 is on, what happens? Okay. If S1 S2 is on means I am not turn on S3 S4. There is no turn on of D1 D2 D3 D4. All that D1 D2 D3 D4 are reverse bias condition. Either S1 initially S1 S2 or S3 S4 is only forward bias condition. But all these diodes are under reverse bias condition only. Okay. We can trigger either S1 S2 or S3 S4. Okay. First I will turn on S1 S2. Remaining all the devices are off state. S3 S4 is off. D3 D1 D4. All these devices are off state. Now tell me, if S1 S2 is on, turn on. This is the direction of flow of current. Just you listen only. No need to draw equivalent circuits, all this. Just you can clearly understand this concept. This is S1, S2 is on. This is the equivalent. No? If the S1, S2 is on condition, this is the flow of current. Now, we are supplying the power to the RL load. Then S1, S2 is continuously conducting. One observation here. I don't want polarity of resistor, mainly concentrate on polarity of inductor. We know that if S1, S2 is on state, inductor is storing the energy. That inductor is, total is V0, but you take this is a, inductor is storing the energy with a polarity plus minus. But continuously you don't allow S1, S2 na. I told already. Once we are operating power electronic circuits means if you want to convert the power or control the power, always we can control either on and off. Then only we can convert or control the power. Here we are converting na. We are converting DC to AC. Inverter means DC to AC. If you are converting DC to AC means you don't allow continuous conduction. You can make on and off. Then only conversion is takes place. Okay. Now, initially I will switch on S1, S2. Then after some time, I will switch off S1, S2. Then again, I will switch on S3, S4. This is S3, S4. Okay. Now S3, S4 is triggered. I will turn on the S3, S4. But point to remember, whenever S1, S2 is turn off, suddenly, even though we can given the triggering to S3, S4, it will not trigger. After turn off of S1, S2, if we give the triggering pulse to S3, S4, even though we can give triggering pulse, but S3, S4 will not trigger. What is the reason? Yes, listen please. During the conduction of S1, S2, inductor is storing the energy. Na? Whenever S1, S2 is switch off, the energy to inductor is disconnected. The supply to inductor is disconnected. We know that. The property of inductor is, then forcibly it reverses its polarity. This becomes negative, this becomes positive. Whenever S1, S2 is switch off, whenever inductor reverses its polarity, because of this negative, D1 is turned on. Because of this negative, D4 is turned on. This is D4 and this is D3. Positive is connected to anode, negative is connected to cathode. Suddenly D3, D4 will comes into the action. We know that for diodes, no need of any triggering pulse. Once the diodes are forward bias, then if there exists a closed path, diode starts the conduction. Now what I am telling, whenever S1, S2 is off, suddenly because of inductor reversing polarity, suddenly D3, D4 comes into the action. Whenever D3, D4 is conducting, the voltage across the corresponding switches is ideally 0. Corresponding switches means for D3 corresponding switch is S3. For D4 corresponding switch is S4. Understood? What I am telling? This is the D3. This D3 diode is conducting like this. This is positive, negative. And this is S3 diode. When the diode is conducting, there is some voltage drop now. Let us assume that 0.5 volts. This 0.5 volts will appear across the switch in the forward direction or reverse direction. Reverse direction. That means practically the corresponding switches are under reverse bias condition. If the corresponding switches are under reverse bias condition, even though we can give the triggering pulse, is it S3, S4 is triggered? No, it will not trigger. Why? Feedback diodes are conducting. Corresponding feedback diodes are conducting. Understood? That's the reason why after turn off of S1, S2, if you trigger S3, S4, it will not trigger because D3, D4 comes into the action due to inductor. When the D3, D4 is conducting, S3, S4 is reverse bias. That's why S3, S4 will not trigger. That's the reason why before S3, S4, which device is conducting? D3, D4 is conducting. This is the reason. That's why before S3, S4, for all lagging loads, before S3, S4, D3, D4 is conducting. Before S3, S4, D3, D4 is conducting. Then how much time these diodes will conduct? Yes. What is the reason for diode comes into the existence? Because of energy stored in the inductor. How much time this D3, D4 will conduct? Yes. This D3, D4 diodes carry the energy stored in the inductor, and that energy is dissipated in the resistor, and some power is delivered to the source, and that energy is dissipated in the resistor. Whenever whatever the energy stored in the inductor that is completely dissipated, then to drive this D3, D4, no energy is there, then D3, D4 is turned off. Automatically it is turned off. Now, which device will trigger? Then S3, S4 is triggered. Now tell me again, if S3, S4 is conducting, this is plus, this is minus. Again inductor storing the energy. In the previous case, the energy stored by the inductor is dissipated in the resistor because of the D3, D4 diodes. Okay. Now if S3, S4 is triggered, then current is flowing like this. This is the direction of flow of current. Now inductor storing the energy. Okay. You don't allow the continuous conduction of any switch now. Then what I can do? After some time, I will turn off S3, S4. Then I will turn on again S1, S2. But whenever S3, S4 is turned off, even though we can trigger S1, S2, it will not come into the existence. It will not trigger because whenever S3, S4 is turned off, suddenly inductor reverses its polarity. Because of this polarity, D1, D2 diodes are turned on. This is D1, this is D2. Positive is connected to anode, negative is connected to cathode. Then D1, D2 is turn on. Whenever D1, D2 is turn on, when D1, D2 will turn on? Whenever S3, S4 is turn off, inductor reverses polarity. Because of inductor reverses polarity, D1, D2 suddenly comes into the existence. During the conduction of D1, D2, corresponding S1, S2 switches are reverse bias. Even though triggering pulse is given to the S1, S2, it will not trigger. That's why before S1, S2, which device will conduct? D1, D2. Before S1, S2, D1, D2. Before S1, S2, D1, D2 is conducting. Then how much time this D1, D2 conducting? Same. Whatever the energy stored in the inductor that is dissipated in the resistor, then D1, D2 will be turned off. Then which device will conduct? S1. Again cycle is repeated. Okay, that is the function of feedback diodes. That is, it may be half bridge inverter or full bridge inverter. What is the function of feedback diode? That is, feedback diodes carries the energy stored in the inductor that is dissipated in the resistor. That is the function of feedback diodes. It may be half bridge or full bridge, any load. But I told that for R load, no need of any feedback diodes. If you have only R load, is it R load means there is no energy stored. Once there is no energy stored, is there any action of feedback diodes? No. That's the reason why for R load, feedback diodes cannot work. Even freewheeling diode also cannot work for purely resistive load. Understood? That is the function of feedback diodes in an inverter circuit. It may be half bridge or full bridge inverter. But again, doubt here, sir. What is the need of carrying the energy stored in the inductor? If leave the energy stored in the inductor, what happens? It becomes unstable operation. Because, for example, if S1, S2 is on, inductor storing some energy. If S3, S4 is on, again inductor storing the energy. Again S1, S2 is on. Again inductor storing energy. How much time inductor will store the energy? Continuously the energy stored by the inductor is increases. After some time, then inductor will be damaged. That's why before switching off next pair of switches, the energy stored in the inductor must be dissipated in the resistor. If you want to make the dissipation of energy stored in the inductor in the resistor means there is some feedback diodes are required. That's the reason why we are using feedback diodes. You don't leave the energy stored in the inductor. Continuously energy stored in the inductor is increases means after some time inductor will be damaged. But that is the problem. That's why if S1, S2 is on, before switching off S3, S4, the energy stored in the inductor must be becomes 0. Then only it is stable out. That every time I told. In any circuit, if the inductor is present, when it is a stable operation, as energy stored by the inductor must be equal to energy released by the inductor. Then only that circuit is stable operation. Otherwise, it becomes unstable operation. For next switching action, it must release whatever the energy stored in one switching action. Before next switching action, it must release. Then only it becomes a stable operation. Understood? That I am writing here. Write as a note. That means it may be half bridge or full bridge inverter. What is the function of feedback diodes? Feedback diode carries the feedback diodes carry energy stored in reactive elements. It may be inductor or capacitor. Energy stored in reactive elements and dissipated in resistor. During conduction of feedback diodes, even though triggering pulse is applied to the corresponding switches, it will not trigger because the switches are under reverse bias condition. Okay. During conduction of feedback diodes, parallel note down. During conduction of feedback diodes, even though triggering pulse is applied, triggering pulses are applied to corresponding switches. It will not trigger. Because switches are under reverse bias condition. Okay, corresponding switches are under reverse bias condition. See another observation here, important. Concentrate. Tell me. Generally, at the starting, we know this. This is S1. This is S4, S3, S2. This load. Okay, load. This is D1. This is D4, D3, D2. This is inverter. S1, S3, S4, S2, D1, D3, D4, D2. At starting, all the four switches are under forward bias condition. S1, S2, S3, S4, all are under forward. Then any switch, any pair of switch you can trigger. Either S1, S2 you can trigger or S3, S4 you can trigger. But I told that don't trigger two switches in one leg at a time. If you trigger the two switches in one leg at a time, there is a possibility of, if instead of S1, S2, if you trigger S1, S4, is there any current is enter into the load? No. this short circuit fault is occurred through the source. That fault is called shoot through fault. There is a possibility of shoot through fault. Now what I am telling here, initially all the switches are under forward bias condition. But point to remember, in bridge inverter, it may be half bridge or full bridge inverter, during the conduction of feedback diodes only, corresponding switches are reverse biased. But remaining case, all the switches are under forward bias condition. When the switches are under reverse bias condition, corresponding feedback diodes are conducting, then that switches are reverse bias. That's why whatever the time feedback diodes are conducting, that time a reverse voltage is applied across the main switches now. But remaining all the time the switches are under forward bias condition. But during which time reverse voltage is applied, corresponding feedback diodes are conducting, then only switches are reverse bias, because the voltage across the diode appear as a reverse voltage across the switches. That's why I told what is the circuit turn off time. In rectifiers, so many times that calculated circuit turn off time, it is the time taken a reverse voltage applied across the switch. During which time reverse voltage applied across the switch here? During conduction of field. That's why the diode conduction time is taken as a circuit turn off time. Clear? What I am telling? During conduction of feedback diode, the corresponding switches are reverse bias. That's why whatever the time the feedback diodes will conduct, that time reverse voltage is applied across the switch. That's why diode conduction time is taken as a circuit turn off time. The definition of circuit turn off time, you know. Understood? Yeah. That means during conduction of feedback diodes, during conduction of feedback diodes, during conduction of feedback diodes, corresponding switches are a reverse bias. Hence, diode conduction time is taken as a diode conduction time. Diode conduction time. Consider as a circuit turn off time. Consider as circuit turn off time TC. Circuit turn off time TC. During conduction of feedback diodes, corresponding switches are reverse bias. Hence, diode conduction time is considered as circuit turn off time. During that time only reverse voltage applied across the main switches. Yes? Let, instead of T axis, I am assuming that it is a omega T axis. If you assume as a omega T axis means, then you take this is pi, this is 2 pi, this is 3 pi now. Let this angle is theta. Diode conduction angle is theta. Diode conduction angle is theta. We take an omega T axis. That means let diode conduction angle is theta. Let diode conduction angle is theta. Diode conduction angle. It may be half bridge or full bridge, same concept. Diode conduction angle is theta. Angle equal to theta. Then what is omega T equal to theta? What is this time is called? You want time now by omega. This time is called circuit turn off time. If the diode conduction angle is theta, then main switch conduction angle. What is the main switch conduction angle, you tell me? Main switch conduction angle. In one half cycle, this is theta means remaining is how much? Pi minus theta. This total is pi. This is theta means this is how much? Pi minus theta. Then main switch conduction angle, it may be S1, S2 or it may be S3, S4. How much? Pi minus theta. See, for example, if in bridge inverter, in single phase bridge inverter, it may be half bridge or full bridge, whatever may be. In single phase bridge inverter, Supplying power to RL load. Supplying power to RL load. Power to RL load. Then the current I naught equal to Im sin omega t minus theta, if it is given like this. Supplying power to RL load means lagging current. These lagging currents are supplied by which one? Diode. This theta is lagging angle na, that's why this theta indicates which conduction angle? Diode conduction angle. Therefore, what is the diode conduction angle, you tell me here? Diode conduction angle is theta. If it is given like this angle is theta, taken as a diode conduction angle. Diode conduction angle is theta. Then what is the circuit turn-off time? Theta by omega. Like this we can calculate. What is the main switch conduction angle? For example, here 30 degrees is given. Diode conduction angle is 30 degrees. You want circuit turn-off time is theta by omega. That you calculate. Understood? Like this also you can solve. This how to calculate circuit turn-off time, how to calculate diode conduction. If it is given like this, how to calculate diode conduction angle, circuit turn-off time, you take main switch conduction angle is, this is pi minus theta. Understood? Okay, this about in detail about half bridge inverter and full bridge inverter. That is FBI versus HBI, half bridge inverter, full bridge inverter versus half bridge inverter. In one side you write FBI, full bridge inverter. In another side you write HBI, half bridge inverter. Tell me, what is the output voltage V0 equal to V0 RMS? That is, you concentrate on V0 RMS. What is the RMS output voltage of full bridge inverter? Vs. That directly gives Vs. What is the RMS output voltage of half bridge inverter? That output voltage is Vs by 2. Yes. How many switches and how many diodes, you tell me? 4 switches plus 4 diodes. Here how many switches and how many diodes, you tell me? Yes. 2 switches plus 2 diodes. Then because of more number of switches and more number of diodes, high switching losses. High switching losses. High switching losses. But this is less switching losses because of less number of switches and diodes. Less switching losses. Next. It requires, I told already, 3-wire DC supply. Sorry, full bridge inverter na 2-wire DC supply. 2-wire DC supply. But this is 3-wire DC supply. I told her this is high cost. Because of 3-wire DC supply, cost is high. It requires 3-wire DC supply. Okay. Then what is the output power? Output power equal to V0 RMS square by R. But what is V0 RMS? Vs. That is Vs square by R. Here what is the output power? Output power equal to V0 RMS square by R. That is Vs square by, what is V0 RMS? Vs by 2 substitute. Vs square by 4R. Then full bridge inverter, efficiency is nearly equal to 100%. But here efficiency is nearly equal to 50% only. What is the peak inverse voltage of full bridge inverter? Peak inverse voltage is Vs. Here also peak inverse voltage is Vs. Okay, these are the differences between half bridge and full bridge inverter that you concentrate. Half bridge and full bridge inverter. One observation here, the output voltage of full bridge inverter, note you take, output voltage of full bridge inverter is 2 times of output voltage of half bridge inverter. That is one observation. Power output of full bridge inverter. Tell me, power output. This is Vs square by R na. but this is Vs square by 4R na. How many times? 4 times. Then 4 times of power output of half-bridge inverter. Very important observations, these two. In full bridge inverter, voltage is 2 times, but power output is 4 times. Okay. This is the concept of half bridge inverter and full bridge inverter. Okay. Then in the next session, we will continue with what is the analysis of half bridge and full bridge. Here I explained some waveforms and what is the operation only. And finally, I given some differences based on the operation, based on the output voltage. Okay, these differences I given. These differences is taken as advantage and disadvantage also, corresponding to each inverter. Okay, there is some disadvantage and there is some disadvantage. Here, this is disadvantage. This is more number of switches and more number of diodes. This is also disadvantage. Here, what is the disadvantage? This is disadvantage. And this is a disadvantage. This is also disadvantage. This is also disadvantage. Which is advantage? Less switching losses, less number of diodes. That is based on these differences only you write which is advantage and which is disadvantage also. Corresponding inverter circuit. Clear? Okay. Note down this. Thank you. In the next session we will continue with analysis on single phase half bridge and full bridge inverter. We want to do some analysis based on the waveforms. Up to now, for single phase half bridge and full bridge inverter, I explained operation and waveforms and some points I discussed with respect to operation. Okay, thank you.